Okay, topic 10, metals. Let's start. Okay, I'm gonna go a bit fast. I mean, I say this every time, but don't go fast. Okay, metals. What are the properties of metals? There's 7 properties, okay? Metals are good conductors, obviously, of both electricity and heat. They're solids, except what? Mercury, right? Uh, and with fairly high melting points. They most have high density, except the alkali metals, which are group 1 metals. We're gonna talk about alkali metals in a sec. They're ductile, have high density, and they sink in water and stuff. Okay, not they're dense. They're dense. Ductile, that means they can be drawn into a wire. Obviously, most wires are made of metals. They're malleable, so they can be made into shapes and sharp objects and whatever. And they have a silvery luster, except copper and gold. This silvery luster basically means it shines and whatever. Okay, metals versus non-metals. They're comparing the properties. Melting and boiling points. Obviously, metals have higher boiling points and melting points, but non-metals have low melting and boiling points. You should know that metals are usually solids, but non-metals are usually gases or solids. Okay. Metals obviously have good electrical and thermal conductivity. However, non-metals have bad electrical conductivity. Okay, non-metals like carbon, oxygen, nitrogen, whatever. What's the only non-metal that can conduct electricity that we know of? Is graphite. Remember graphite. Someone's gonna say, "No, what's graphite? How is that a non-metal?" My graphite, remember, is carbon, right? Carbon linked to carbon linked to carbon, 3 carbons, and then linked with from one layer. Like remember, it was triangle. Okay, then it's 1, 2. Oh wait, this is 3. Yeah, yeah. Okay, then 1, 2. Okay, and then it's linked to a layer of carbons that's down. Remember the network solids, guys? That was the graphite. So graphite is a non-metal because it's made out of carbons. Thermal conductivity, come in. Metals are obviously good, but non-metals are bad, except diamond. Not graphite, except diamond. Okay, diamond is a good thermal conductor. Malleability and ductility, obviously metals are both malleable and ductile, but non-metals are neither malleable nor ductile. Strength and hardness, obviously metals are usually strong and hard, and they have high density. And non-metals are soft, except what? Diamond. Yeah. Ability to produce sound. Metals produce sound. Think about bells. Bells are made out of metals. Non-metals are not sonorous. Sonorous basically means it produces sound. Appearance, metals are gray, except copper and gold. They can be polished to give a shiny surface. Okay, so this silvery luster, يعني doesn't mean shiny, يعني it's like this grayish appearance. Okay, they can be polished to give a shiny surface. The appearance of non-metals have different colors, but they're usually dull, so they don't give color. Okay. Okay, so this is just a compare and contrast. You should know them and read over it quickly. It usually comes multiple choice. Okay, group 1 alkali metals. Okay, group 1 alkali metals, if you open the periodic table over here, so this is group 1, right? So these are what we call the group 1 alkali metals. Okay, hydrogen not included. Lena crypsis, remember these? Okay, so these are the group 1 alkali metals. What about them? They're group 1, so you should assume them to be the most reactive. Okay, so they are very active. The first property you should know about the group 1 alkali metals are that they're soft. If you take a look, by the way, they're very soft. Let me show you 1 second. So this is I'm pretty sure many of you have seen this channel before, but this is sodium. If you try cutting it with a knife, look how easy it is. Look, it's very soft. Okay, so it's kind of like slime. So basically, you need to know that the group 1 alkali metals are soft. Okay, they're soft metals. ماشي? Easily cut by a knife, and they exhibit these general trends down the group. So as you go down the group, the reactivity increases. Okay, and this is shown by the reaction of the water. Okay, and usually when you compare reactivity, they react it with water and see which one's more reactive. Melting points decrease, density increases. So as you go down, if you want to take notes, that would be good. So as you go down, what's happening? Melting points decrease. Okay, reactivity increases. Okay, it gets more reactive. Like مثلا francium, by the way, is the most reactive metal in the whole periodic table. Okay, reactivity increases and what? Density increases. Okay, so you should know this. طيب, moving on. So they're gonna say أكيد list. Okay, they have relatively low densities, so they are usually lower. They have lower densities and melting points compared to other metals. They have shiny, lustrous surface when freshly cut, but quickly tarnish when exposed to air. So, like when I showed you the sodium now, if you go back, it was kind of shiny when they cut it. Okay, so list 4 properties of alkaline metals. Very easy. They're soft metals. They have lower densities. Okay, easily cut with a knife. Have shiny, lustrous surfaces when freshly cut. They tarnish quickly on exposure to air, so its shininess vanishes after exposing to air. And they have low melting and boiling points compared to other metals. Okay, and then why are alkaline metals never found in their pure form? Because they are very reactive. They must be stored in oil or something else. Okay. Okay, you are supplied with 3 samples of white powders and told that they are nitrates of lithium, sodium, and potassium. How do you identify Li, Na, and K? If let's go back to chapter 2, how do you identify them? Using the flame test. Lithium gets you a crimson red flame, sodium gets you a yellow flame, and potassium gets you a lilac violet flame, right? So you perform a flame test and you're gonna get these results. So anytime you're asked to differentiate between the alkali metals, you go for flame test. Transition metals, أصلا metals in general, huh? Transition metals, okay, this is a section by itself. You need to know about the transition metals. You need to know أول شيء they're harder, denser, and have higher melting and boiling points than other metals. Where are the transition metals? These are the transition metals over here. From scandium over until coperincium. These, okay? These are my transition metals. So you should know that they have higher melting points and boiling points. They're harder. Harder, denser, have higher melting points and boiling points. Okay. What are the chemical properties? You should know. أول شيء, they form colored compounds. Okay, they form colored compounds. Like مثلا copper sulfate is blue, right? This is hydrated copper sulfate. Iron hydroxide, it's rusty brown. Remember, this is from chapter 2. K2CR2O7, it's orange. Potassium manganate, it's purple. Remember? So these are the transition metals: copper, iron, chromium, and manganese. Okay, you can see them in the periodic table if you don't believe me. Type. So what else do we know about the transition metals? Is that they form ions with multiple oxidation states. So I'm pretty sure you guys have seen copper. No, one of the most famous ones is iron. Iron, we have 2 plus and 3 plus. This was coming in chapter 2, salt preparation, and sure salt as they had test chemical analysis. Fe2 plus would form green precipitate. However, Fe3 plus would form dirty brown. Right? So this is one of the prime examples that transition metals form ions with multiple oxidation states. Okay, and these are other ones: copper C1, C2 plus, cobalt is 2 plus, 3 plus, manganese can be 2 plus or 4 plus. Okay, what else? They have catalytic properties. Okay, we saw in chapter 2 in the catalytic converter that you use transition metals such as rhodium, palladium, and platinum. Okay, so over here they're giving us some examples. Iron is used in the Haber process for the manufacture of ammonia. Remember, in the Haber process, the catalyst used was firing iron. Vanadium in the contact process to form sulfur. Remember, we said that the catalyst was vanadium oxide. Manganese is the catalyst in preparation of oxygen from hydrogen peroxide. Remember, in the lab, using the catalytic decomposition of hydrogen peroxide to prepare oxygen, the catalyst was manganese oxide. If you go back to the air topic 3, air, topic 2, sorry, air. Nickel is used in the hydrogenation of alkenes to produce alkanes. So nickel, another transition metal, is the catalyst in the hydrogenation of alkanes to produce alkenes. This was in topic 5, organic chemistry. Okay, so we went over all of these. As well as in the catalytic converter in topic 2, they mentioned palladium rhodium, and platinum, which are used in the catalytic converter. Anyway, what are transition metals? They are, let's take a look at the answer key actually. I'm not going to say anything. They're located between groups 2 and 3, which are columns 2 and 13. And they are metals that form at least one ion with unpaired electrons. I'm not too sure what they mean by this one, but in case it comes multiple choice. So a transition metal is located between what? Between group 2, so between group 2 and 13, okay? A column 2 and 13, which is all the way from column 3 till column 12. With the periodic table, this is very easy to identify. And they are metals that form at least one ion with unpaired the electrons. I don't get what this means. But anyways, moving on. List 6 characteristics of transition metals. These we must memorize them all the way down at 29. We should know that they're harder than other metals. They have higher melting point and boiling points. They are denser than other metals. Right, they're denser, harder, denser, higher multi point, higher boiling point. They form colored compounds, they form more than one oxidation state, and they have catalytic properties. Okay, reactivity series. Transition metals are less reactive than group 1 and 2. Metals are arranged in a decreasing order of their reactivity, in decreasing order of the tendency of a metal to form its positive ion. The more reactive a metal is, the easier it forms its positive ion, and the harder it is to thermally decompose its compounds. So basically what this is trying to say is, okay, yeah, hello, we'll go here. Displacement reactions of metals and their compounds can be used to work out the reactivity series. Okay, this is a lot of yap, but I have to explain. Okay, this is the reactivity series, okay, which I have memorized as Canalica. I don't know why she didn't put sodium. Yeah, she didn't put lithium. Canalica meets all zebras first. No person here could argue. Okay, so these are like K is potassium, Na is sodium, lithium isn't here, I don't know why, calcium, magnesium, aluminium, zinc, iron, nickel should be between, should be before lead, and then hydrogen, copper, silver, and gold, it should be here as well. But I don't have it in mind, since it's very, very little, like its reactivity is so little. Okay, anyway. So this is how they work out the reactivity series. So when they put zinc plus copper sulfate to produce zinc sulfate plus copper, you should know these observations. These are displacement reactions. Remember displacement reactions from, I think it was chapter 2 or chapter 3 or maybe chapter 4, the redox chapter. But anyways, when you have a metal more reactive than another metal, they swap. Okay, so it's gonna take the sulfate. Okay, so it's going to become zinc sulfate and the copper will be alone. Okay, so the observation you're going to see in a reaction like this, because they might get it in the written and tell you, okay, what's the observation? Copper sulfate, the blue color will disappear, right? And the red-brown solid is deposited, which is the copper. Since zinc can replace Cu2 plus from its solution, then zinc is more reactive than copper. So this proves this reaction. Mathalan, she might give it to you and say, what can you conclude from this reaction? You would say zinc is more reactive than copper sulfate. Anytime you see that an ion displaced the other ion, you see how it displaced it, it took it out and took its place, that means it's more reactive, it's stronger. Okay? Okay. Experiment 2. Here, copper plus silver nitrate to produce copper nitrate plus silver. Okay, so as you can see here, it displaced the silver. Okay, so what is the observation? You're going to see a silvery deposit, which is the silver. Okay, and the colorless solution will turn blue because of the formation of Cu2 plus. Right? It's going to turn blue because of copper nitrate now. So since copper can displace the silver ions, what does that mean about copper? It's more reactive than silver. Okay, that is what these reactions are proving. From the results of 2 experiments, we can place the 3 metals in the following order: reactivity Zn, Cu, Ag. Zn being after many experiments, they built the reactivity series. Okay, and this is kullu habal. I have it memorized. Canalca meets all zebras first. No person here could argue, and that is the reactivity series memorized for me. Okay, I don't even think about any of this. Okay, some metals react immediately once exposed to air, forming oxides like the alkaline metals. Some need to be powdered and heated like iron. However, in the presence of water, iron will slowly react with oxygen and air, forming the oxide we call rust. You guys know, when you add iron, when you add to iron oxygen and water, what's gonna happen to it? It's gonna rust. Okay, and in chemical terms, it's iron oxide. You don't need to know this. What do you need to know? Rust does not stick to the iron surface but flakes off. You need to know this. Aluminium doesn't rust, but what happens? It reacts very quickly. It forms aluminium oxide like iron does. But what happens is this aluminium oxide, it doesn't spread and rust throughout the hook. It doesn't continue rusting. Like if it rusts here, it doesn't continue and spread rust into the whole metal. No, بالعكس. What's cool about aluminium, why they use it, is because if you have an aluminium rod and it rusts only on the outer layer, and this outer layer doesn't spread into the aluminium. What happens? No. It doesn't spread. It forms what we call a protective layer. So this aluminium, it forms a protective layer and sticks to the metal surface, protecting it from further reacting. This makes aluminium appear less reactive than it actually is. Maybe 2 or 3 questions came in the CA about this in week 11. The reaction with oxygen can be used to compare reactivity of metals. For example, Lina, Kirby, and all react with air, Li tarnishes slowly, Na quickly, and K very quickly. Again, if you know the reactivity series, you know this already. Canalica meets all zebra spurs. K is more reactive than A, and A more reactive than Li. Okay, if you know the reactivity series, you don't even have to read any of this. Okay, the reaction with oxygen. This came typing in week, I think 10. Okay, or 9, I don't know. Or 11, I'm not sure, but it came typing. Okay, you need to know this. If you want to react something with oxygen, let's say you don't know, K plus oxygen O2 to produce, what does it produce? K is plus, O is 2 minus, so what compound will be produced? K2O. طيب, you need to balance. You have 2 potassium, so you put a 2 here. Okay, هلا you have 2 oxygens, so you have to put a 2 here. طب هلا you have 4 potassium, so you make this a 4. Okay, as you can see here. So here, you should know, you don't have to memorize this at all. You can do it all manually, the same way I did it now. Let me do one more. Sodium, Na plus O2 minus. So the compound being formed will be what? Crisscross. You're going to get Na2O. So add the reaction Na plus oxygen to produce Na2O. Same balancing. It's going to be like this. Okay. Heck. Okay. Very easy. You don't have to memorize anything. Okay. What do you need to know? Just how to write the reactions. If she asks the colors, of course, K will be purple lilac, Na is yellow flame, calcium is brick red flame, Mg, if she asks, is a white flame. You should know aluminium burns less strongly. Why? Because we said that aluminium provides, aluminium has a protective layer on the outside, right? So it's gonna burn less strongly provided the oxide layer is removed. Zinc is less strongly, iron is less strongly, lead needs to be heated. Copper does not burn but forms a black layer. Okay, you should know this. Okay, type. Again, if you know the reactivity series, Canalica meets all, small a, meets all zebras. First, no person here could argue. Copper and silver are lower than hydrogen, so they can't react. مثلا lead is so little, so if they were to ask you which one is little and needs heat, always going to be lead, because look how little its reactivity series look how little its position is in the reactivity series. So K and A, they react vigorously. Aluminium, it's further down, so to react but just a bit less strongly. Zinc and iron as well, they're going to be a bit less strong. Okay, so again, if you have the reactivity series memorized, all of this كله على الفاضي. Okay, you can just, if you have the series memorized, you don't even need to memorize any of this. Okay, other than the colors here. Write the chemical equation for each of the following reaction. Okay, this came in the CA. Okay, they're right here, so I won't do them. Okay, you can pause and take a look. I already did sodium. You use the same logic for magnesium and aluminium. Okay. Okay, reaction. Okay, this, I spoke about this in topic 2, I think, because it was in the course division for some reason. But you need to know which ones react with water and steam, and which one can react with steam only. Okay, so if a metal is very reactive, it can react with liquid water. If it's not that reactive, it can only react with steam. Steam is gaseous water, right? So which ones can react, which one can't? Okay, the ones that can react with liquid water, okay, which is cold water, are Knalika, Mg. Okay, the ones that can react only with steam are everything after Mg. Mg is included in both liquid water and steam. Why? Because هي هيك is this reactor. حطيت لك note, okay. Mg can react with both, but it reacts very slowly with cold water, but faster with steam. Why do you think it reacts faster with steam? Isn't steam hot, right? Isn't steam hot? So when something is hot, doesn't it have more energy? Yes. So that's why the less reactive metals, such as Al, Zn, Mg, and Fe, which are further down the reactivity series, since they're less reactive, they need more energy to actually react. Therefore, it can only work with steam. Okay? But these ones, Knalika, okay, although she didn't say Li, the teachers added it later in the notes. Knalika, they're already very reactive. So do they need energy to react? No. So adi, they can react with cold liquid water. They don't need the hot energy from steam. But don't get me wrong, they can still react with steam. But no, they can also react with cold water. Type. Is there a difference in these reactions, Walid? Yes, there is. Okay. Knalika, when they react with liquid water, okay, or steam, they form the metal hydroxide plus hydrogen gas. Okay. However, when they react with gaseous water, the steam, the rest of the metals, they don't form a metal hydroxide, they form a metal oxide. Okay, so a prime example is actually the reaction of zinc. So zinc plus liquid gaseous steam will get you zinc oxide plus hydrogen gas. Okay, that's it. Very easy, not too hard. Okay. The reaction with water can also be used to compare reactivity. For example, Li, Na, and K all react with water, producing the hydroxide and hydrogen gas. However, Li reacts steadily, okay, Na strongly, and K violently. So see here, she mentioned Li, but here she forgot to write it. I don't know why. Okay, generally, the reactivity of metals decreases down a group, and group 2 metals are less reactive than group 1. I don't know what they mean here, because in group 1, we said that it increases down the group. Here she's saying it decreases. I think she means as you go down the groups, 1, 2, 3, 4, 5, they become less reactive. So 2 is less reactive than 1. I think that's what she means. Okay, so group 2 metals are less reactive than group 1. Okay, list some of the chemical properties of the alkaline earth metals. Say whether they react with cold water and how the reactivity varies down the group. The alkaline earth metals are group 2. Okay, the group 1 ones were alkali metals. Alkaline earth is group 2. But let's take a look at the chemical properties of the alkaline metals, CQD7, over here. Okay, alkaline earth metals, they are highly reactive. The reactivity increases down the group, as we agreed. In general, group 1, as you go down, it increases. Group 2, as you go down, it increases. Okay, when they talk about their reactivity with cold water and how the reactivity varies down the group, let's take a look. We ignore beryllium. Mg, we know it reacts with cold water, right? But it also reacts with steam. Here they're asking about the reaction with cold water. Which one here in group 2 reacts with cold water? Only magnesium. So let's see, magnesium reacts with steam to produce the oxide and hydrogen gas. Calcium, which is more reactive than magnesium, reacts with liquid water to produce calcium hydroxide and hydrogen. Calcium also reacts, Remember the ones here, the ones that react with cold water. Remember we said they're Knalika and then Mg. Okay, so the ones that react with cold water from group 2, which ones are they? Which ones here are group 2? It's just Mg and Ca. But Mg is very slow, so I think that's why in the solution she said, what did she say? Magnesium reacts with steam, not liquid water. Okay. Calcium. Okay, this is wrong. It reacts with liquid water. خلاص, ignore this solution. I don't know why it's like this. Just know alkaline earth metals are highly reactive. The reactivity increases down the group. Okay. You should know that magnesium does react with steam and liquid water and liquid H2O. Okay, but which one does it react with to produce the oxide To produce the oxide, remember, to produce the oxide, I said it's with steam. But if you want to react with liquid cold water, you're going to produce the hydroxide. Okay? If you react with the liquid water. Okay? Calcium, which is more reactive than magnesium. So calcium, does it react with cold liquid water? Yes, we said it does. To produce, in this case, calcium hydroxide and hydrogen. Okay. You should know that the alkaline earth metals also react with oxygen to produce the metal oxide. Like Mg, when it reacts with O, Mg plus O2 produces what? MgO, right? Or Ca plus O2 produces CaO, right? So these are the reactions. So here, يعني مثلا, these would come multiple choice, okay? You just have to select. They react with chlorine to produce the ionic white solid metal chloride. Okay, in case they come, they were in the course revision right here. Pretty self-explanatory. You are supplied with a sample of white powder and told that it is calcium chloride. Explain how you can identify the cation in the powder. How can you figure out that it's calcium? Okay, and I'm thinking flame test, but let's see. Yeah, prepare a solution of the salt, dip a wire, and place it in a clean flame. What flame do you get if it's calcium? If it's calcium, you get brick red. Here they said orange red, but brick red is also correct. Okay, so if you want to identify a cation, usually what do we do? Flame test. Write equations for the reaction of calcium with water and oxygen, and write an equation to show how lime water is used. Okay, forget about lime water. هلا. Calcium with water. Okay, Ca plus water, H2O. Okay, calcium is solid. The water, is it going to be liquid or gas? Remember, we ask ourselves, what are the ones that react with liquid water? Kna, Li, Ka, and magnesium is included as well. So calcium will react with liquid water, so it's going to be liquid. But since it's reacting with liquid water, will it produce a hydroxide or just the oxide? We said if it's with a liquid, it's going to produce the hydroxide. Okay, Ca2 plus OH minus, crisscross, you're going to get CaOH2, huh? Plus hydrogen gas. You can't forget the hydrogen gas. This is, I think this is aqueous, I think. Let's take a look. Yeah, it's aqueous. So Ca solid, they forgot to put gas for hydrogen. Plus H2O liquid, and to produce hydrogen. If you put the other reaction, you reacted it with gas, you're not even gonna get half a mark, you're gonna get 0 marks, okay? With oxygen, how do you react calcium with oxygen? Ca plus O2 to produce CaO. Why is it CaO? Because it's Ca2 plus and O2 minus. The charges cancel, huh? Okay, so you're gonna get CaO. Balance it. You need to put 2 here and 2 here. Okay, هيدي solid, هيدي gas, هيدي it should be solid. Okay, write an equation to show how lime water is used to test for carbon dioxide gas. State any expected observation. Obviously, the observation to test for carbon dioxide gas and lime water would be lime water turning milky. But let's take a look. We mentioned this before, I think. Okay, so the calcium, lime water, by the way, lime water is calcium hydroxide. Okay, lime water is just calcium dissolved in water to get calcium hydroxide. So this is what lime water is. Okay, so this lime water, it's gonna react with the carbon dioxide, and what does it form? It forms a CaCO3 suspension. This is what causes the solution to turn milky white. Okay, because the lime water is calcium hydroxide. When it comes into contact with carbon dioxide, it forms a CaCO3 milky white suspension that causes the solution to turn milky. Okay, so in case it comes in, you're never gonna be asked to write these types of reactions, but you just need to know them in case it comes. Okay, reactions of metals with an acid. Moderately reactive metals react safely with acids, forming the metal salt and releasing hydrogen. Okay, we know metal plus acid gets you metal salt plus hydrogen gas. This is very easy. Okay, type reaction with water, reaction with acid. Okay, let's take a look. So with water, اتفقنا انه the ones with water are كناليكا, and magnesium is included as well, but it's slow, right? So with water, so these react with cold water, cold water, cold water, cold water. But magnesium, they didn't write the reaction with cold water. They wrote the one with steam because they said it burns readily in steam. We told you that magnesium, although it does react with cold water, it's gonna be very, very slow. So that's why they usually react it with steam. Okay. Then after magnesium, what do they react? Do they react with cold water anymore, liquid? No. After it, they all react with what? Gaseous steam. Okay. The properties, obviously, potassium being violent, sodium being violent, and then calcium being reacts well, and then magnesium becoming slow, and then yellow and hot and white and funky. Okay, read over these, know their properties. Okay, you need to know their properties. Okay, iron reacts when steam is passed over hot metal. Okay, what do you need to know? You need to know that lead, copper, silver, and gold have no reaction with water nor with an acid. Okay, you need to know this. Type with an acid, obviously all of them will react with an acid. Metal plus acid gets you the salt plus hydrogen gas, right? But you should know that obviously Canalica meets algebras first. As you start with a higher metal like potassium and sodium, the reaction will be very violent. Okay, so therefore it should never be tried in the lab. Okay, these reactions should never be tried. So usually with acid metal reactions, they use a less reactive metal such as magnesium. Okay, they use magnesium usually. Okay, they even calcium they don't use it. Okay, Mg disappears, colorless solution. Slow to react with cold acid, bubbles form when heated. Al disappears and colorless solution. Very easy. So what do you need to take in from this table here? You should know that the ones that react with cold water, as we mentioned previously, were Canalica and magnesium is slow. This is what you should know. Okay, you should know that lead, copper, silver, and gold, no reaction. Okay, you should know that they all with acid, but Canalica are too vigorous, very vigorous, so it's not gonna be tried in the lab. Okay, that's it here, very easy. Which metals react with water and which react with steam only? Which metals do not react with water or steam? Okay, so which metals react with water? With water اتفقنا انه it's Canalica. Okay, which react with steam only? And magnesium. With steam only steam, it's gonna be everything after. Meet all zebras first. Okay, these ones are with steam only. Okay, so and I just memorized the reactivity series. Canalica meets all zebras first. No person here could argue. Which metals do not react with water or steam? Which don't react with water and steam? Obviously, copper, silver, and gold. But I think I remember our teacher saying that she removed lead from the solution here. Oh no, better she put it. Okay. Okay. So it's wrong to say Mg reacts with steam only because it reacts with water as well. But it's just faster with steam. Okay. But you should know that magnesium is very slow with liquid water. Even though it does react, it's very slow. Here, as we wrote, she didn't include gold in the answer key. Adi, that's fine. Okay, type. The diagram below shows the apparatus used to test for the reactivity of sodium, iron, and silver with steam. Which of these metals can react with steam to form hydrogen gas? So أول شيء, let's take a look. Does sodium react with steam to form hydrogen gas? هلا it can, but I don't think she's looking for that. I think it's gonna be, it can react. Sodium can react. It can react, of course it can react. Iron, does it react with steam? Remember, the ones we said that react with steam only are Al, Zn, and Fe, and Mg as well. Okay, so iron, Fe, obviously it can react with steam. Silver, can it react? Remember, Cu, Ag, Pb, and Au. Copper, silver, lead, gold. These ones don't react, so silver should not be able to react. So it should be E, but I don't have a feeling it's wrong. But let's see. Okay. Someone might say, طب sodium, Walid, you said sodium reacts with water. Canalica recap. You said وليد خلاص it reacts with water. How is it reacting with steam? أخي أكيد if it reacts with water it's gonna be able to react with steam. بس ونحن we're saying it can react with water. خلاص if it can react with steam it doesn't mean if it reacts with water it doesn't mean it can't react with anything else. We're just saying oh it can react with water if it wanted to. Okay. طيب CQD 12. Which metals react with dilute HCl? Pretty much all of them except copper. Remember, with the acid, all of them except copper, silver, gold, and lead.
I did.
Which are not able to react with 1 molar HCl. So these ones are not able to react with HCl. Which metals? If they ask you to name the metals, you need to know the reactivity series. K, Na, Kna, Li, Ka, Meat, all, zebras, first, no. And then person here could argue you can't do it because these don't react. Okay, so these ones are the ones that react. Let's take a look. What did she put? Metals that react, Knali, Ka. She doesn't, I don't know why she's not mentioning Li anymore. So Knali, Ka meets all zebras first, and you can put nickel as well, huh? Metals that are not able to react of PbCu and Ag, and she's also not mentioning gold, Au. I don't know why, even though it's correct. The table below gives information about 3 different metals. What is the order of reactivity of the above 3 metals? Okay, so let's take a look. P, its metal oxide is reduced upon heating with carbon. Okay, and for P, it can react with an acid. For Q, it's reduced upon heating with carbon, but it can't react with an acid. Okay, can't react with acid. So immediately when you see that something can't react with an acid, that means it's the least reactive. Okay, and then here R, it can't be reduced, but it can still react with an acid. So obviously the most reactive one here will be P. So it's either gonna be, okay, well, it's obviously gonna be B. Okay, but if it can't, it's gonna be B. خلاص, I'm not gonna continue. Why is the answer B? Because P is the most reactive metal, because it can both react with carbon and nitric acid. Yeah, it's pretty obvious. QRP. C is the answer B. What question is this? 13A. Okay, I just I think I'm a bit stupid. If something is being reduced by carbon, that means carbon is more reactive than whatever metal this is, right? So if R can't be reduced by carbon, that means R is more reactive than carbon. These two are being reduced by carbon. Therefore, these two, P and Q, are less reactive than carbon. So that means R is the most reactive from P and Q. Okay, so R is the most reactive from P and Q. So we're either on A or D. Type. We need to now know which one's more reactive, P or Q. Type. P can react with an acid, but Q can't react with the acid. Since Q can't react with the acid, but P can, that means P is more reactive than Q. Okay, so تفعلنا انه R is the most reactive, and then P is more reactive than Q. So if R is the most reactive between P and Q, and then P is more reactive than Q. Okay, so the least reactive is Q, the most reactive is R, and then P is in the middle. So the answer is A. Write equations for the reactions of aluminium with air, HCl, and steam. Okay, when we say reaction with air, that means with oxygen. Okay, so aluminium plus O2 to produce Al2O3. Why is it Al2O3? Because Al is 3 plus, O is 2 minus, crisscross, you get Al2O3. Okay. Balance this, you're gonna get 2. Here you put 3. Here you put 2, so you put a 4 here. Okay, so this is the reaction type. HCl, aluminium with HCl, aluminium plus HCl, metal plus acid gets you metal salt, so AlCl3 plus hydrogen gas, right? Metal plus acid. Okay, this is pretty easy. With steam, you guys know aluminium, it reacts with steam, صح? It doesn't react with liquid water. So aluminium plus steam, which is H2O gas, okay, to produce, remember with steam, you produce metal oxide or hydroxide? Metal oxide. So you're gonna get Al, aluminium oxide, which is Al2O3. How do you know it's an Al2O3? Because Al is 3 plus, O is 2 minus, crisscross, you're gonna get Al2O3. Okay, plus always hydrogen gas. Okay, you need to balance this. So you need to put a 3 here, and you're gonna put a 3 here. Okay, and you're gonna put a 2 here. Let's take a look. 37. Okay, yeah, there you go. I didn't balance the previous one, huh? This is how you balance it. طيب, observations for reaction of metals with water. Okay, so the reaction of NaKli. These are our big boys. Kna-Li. Okay, these are our strong metals. طيب, what happens since they're the strong big boys that are very active? Obviously, the first thing that happens is a small explosion will occur. So obviously a piece of metal will become a ball, you put it on the surface of water, and a small explosion will occur. So since it's very active, you're gonna get an explosion. It's gonna form a colored vapor. You guys know when an explosion happens, it's not just take, but it explodes. It forms like a small flame. Okay, this small flame, since we're talking about K, it's gonna be what? Lilac, right? So due to K plus ions, it will be lilac. If it was Na, it will be yellow. If it was Li, it will be crimson red. Obviously, the piece of metal will decrease in size because خلاص, it's dissolving in water, right? And it's reacting. How about the pH of the water? The pH of the water will change from 7 to 14. Why? طب انت when you're reacting NaK and Li with water, you form the metal hydroxide, right? If it was Na, it was NaOH. If it's K, it would be KOH. If it's Li, it's LiOH. But my point is, you're going to form this metal hydroxide. Isn't this basic? Isn't this a base? Yes, so for that reason, the pH will jump to 14. Okay? Okay, هلا you have the reaction of calcium with water. Now, remember, with water, you can only have KNaLiCa. Okay? These are the big three that we mentioned here. Okay, they do explosion وما بعرف شو مدري شو, or changes from 7 to 14. طيب, Ca also reacts with water, you can't forget that, but it's further down the reactivity series, so will it be as vigorous as the big KNaLi? Let's see. The reaction of calcium with water, obviously the piece of metal will sink. It's going to move up and down due to the bubbles of hydrogen gas being formed, and the solution will turn milky or white due to the formation that has due to the formation of calcium hydroxide that has a pH of 11. So let me explain what's going on over here. With calcium, it's not going to explode. It's just going to sink and start forming hydrogen gas bubbles, right? Because calcium plus water produces calcium hydroxide, right? Metal hydroxide plus hydrogen gas. طيب, it's going to bubble and form hydrogen gas. You should know that the solution will turn milky or white. Why? Because you're forming calcium hydroxide. Whenever you have calcium hydroxide in water and there's some metal left over, it will turn milky white. Why? This calcium hydroxide will react with water and form calcium carbonate, and that calcium carbonate will act as an acid. No, it won't. Metal plus metal carbonate plus, wait, never mind. The calcium hydroxide has a pH of 11. Okay, just know that it turns milky or white. I want to know why though. Wait. I just understood why. I'm so slow. The calcium hydroxide itself is a white precipitate. Okay, remember guys, calzone and the reaction calzone. Remember, calcium will form a white precipitate that's insoluble, right? If you remember this from term 1. Okay, so anyways, if you didn't know it, well, now you know it. Okay, this is what causes the reaction of calcium with water to be different than that of sodium, potassium, and lithium. Okay, so the reaction of calcium will form a milky white precipitate. طيب. Extraction of metals. Okay, the extraction of metals it's a bit long, but it's easier than the other one. There's less memorizing. Okay, metals are not usually found in the pure state, so they usually exist as an ore. If you play Minecraft, you know what I'm talking about. Most exist as ores containing minerals mixed with an unwanted rock. The ease of obtaining the metal from its ore is related to its position in the reactivity series. If it's more reactive, then it's more difficult to obtain the metal from its ore. Okay? The method of extraction depends on the reactivity of the metal. Okay? Reactive metals, electrolysis. Okay? These ones, you're going to do electrolysis of the molten chloride. Okay, but aluminium, you're going to do the electrolysis of molten oxide. Okay, this is just the reactivity series, huh? And then the rest, zinc, iron, tin, lead, copper, you're going to do reductions. These metals are below carbon in the reactivity series, so they can be obtained by heating their oxides with carbon. When you heat their oxides with carbon, since carbon is more reactive than them, the carbon will displace the oxide and you're going to be left with the metal. So let me go through this one by one. Okay, and by the way, silver and gold are found as pure elements because they're not reactive. Huh? Type, look, the molten chloride, these ones you need to do electrolysis. Kna, li, ka, mg. These ones you do electrolysis as well as aluminium. Okay. This one you do it as a molten oxide, but these ones you do it as molten chloride. Okay, so KCl, NaCl, LiCl, and so on and so forth. So Al, you do the electrolysis of Al2O3. Okay, type the rest of them, zinc, iron, tin, lead, copper. These ones, when they exist as metal oxides, right? If you heat it in the presence of carbon, the carbon will displace it. Since carbon is more reactive, it's going to displace it and it's going to leave the metal alone. You see how that worked? Okay, so you just need to know as سريع. هلا they barely ask about this stuff, guys. They don't ask it أصلا. But here the process is what they ask. Okay, the extraction of iron. Okay. I'm gonna go through step by step what you need to know, what is asked usually in exams, what do they care about. Okay, to extract iron, okay, you start with I'm gonna leave all the irrelevant stuff. You start with Fe2O3. Okay, it's, in other words, they call it hematite. Okay, so if you see hematite, it's just iron oxide, Fe2O3. Like we said, these elements all exist as ores, right? Okay, iron is one of them. So to extract it, they exist as ores, and in this case, they exist as an oxide. It's called hematite. How does this work? So you have what we call a blast furnace, and from the word blast furnace, there's a lot of heat going on. Okay, so how does it work? You just basically heat and heat and heat the iron until you end up getting some leftover iron. And whenever you see heating and heating in the presence of carbon, this is called reduction. Okay? You need 3 raw materials. Okay? We need obviously the iron itself, the hematite, the Fe2O3 or Fe3O4. And since we're reducing it in the presence of carbon, you need to have some carbon. They call it coke. Okay? Coke is used instead of coal. Okay? Coal is also another source of carbon, but they use coke. Okay. Anyways, the third raw material that they use is CaCO3. Okay, limestone. How does it work? You start أول شيء, there's a set of reactions. Okay, let me scroll down. Okay, so I'm gonna go through the steps. Powdered iron, coke, and limestone are fed into the top of the furnace. You just throw it in, and they blast hot air. Okay, so here is how it works. Okay, أول شيء, the first thing that happens is the coke burns in oxygen. Okay, you get carbon plus oxygen to produce carbon dioxide plus heat. Okay, انسى. The first reaction, you need to know this. Coke plus oxygen to get carbon dioxide. Then this carbon dioxide reacts further with more coke, since there's a lot of coke, okay? It reacts with more coke. So now CO2 plus C, it becomes C2O2. But do we write it like that? No, we factor out the 2 and it becomes 2CO. Okay? So there you go. You now have 2 COs. طيب. This CO is now what reacts with our lovely iron. Okay? So our iron, it needs to react with carbon monoxide. So it has to go through these 2 steps before it can react with this carbon monoxide. Now to react with carbon monoxide, we just react it and we end up with iron plus carbon dioxide, right? طلعنا الأكسجين من الإيرون, we took it out and became CO2, right? We have Fe now. Okay, what do you need to know? These 3 reactions are a must to know. You must know them, okay? I will not be surprised at all if she gets the written part, just this. This is one of the written parts. I won't be surprised, okay? But this is the first thing. These 3 reactions you need to know. There's more. There's 2 more down here. What do you need to know? If they ask you about the states, obviously the iron is an ore, and the iron produced will be molten, so it's liquid. Okay, if يعني, because maybe she might ask for state symbols in the reaction. Anyway, coke is used instead of coal because it is a better fuel than coal. Okay, this she could get this. Why is coke used instead of coal? It produces more heat and causes less pollution because it contains less amounts of sulfur. طيب. Dense molten iron runs to the bottom of the surface of the furnace dense molten iron runs to the bottom of the furnace and is run off, right? So خلاص, we're done. Our iron is going to the bottom and it's running off. خلاص, it's leaving. طيب, we have a small problem. Okay, there are gonna be many impurities in this iron. Okay, and they talk about it here. They call it pig iron. Okay, but anyway, there's gonna be many impurities in this iron. And do we want impurities? Never, right? We always want it to be as pure as possible. So for that reason, we go through 2 more reactions that purify the iron. So the first impurity in it is sand, which is SiO2. This is the major impurity. How do we remove it? This is where the third raw material, limestone, plays its purpose. Okay? So over here, this limestone, it removes the SiO2. How? Okay, limestone is calcium carbonate. Okay, since it's so hot, it gets broken down into CaO and CO2. Okay, this CaO acts as a base, right? It's a metal oxide, so it's a base. So it reacts with sand, silicon dioxide, this is acidic, by the way. Okay, as an acid-base reaction to form a liquid called slag. Okay, so CaO reacts with SiO2 to produce CaSiO3. You just combine them together, okay? And this is called calcium silicate. Okay, it's called calcium silicate. So what do you need to know? You need to know this reaction, this reaction, this reaction, this reaction, and this reaction. If you know these 5 reactions, you know them, you understand what's going on, you know this topic 100%. Okay? This calcium silicate is called slag. Okay, this slag runs off as well as an impurity. It leaves as an impurity. With the iron is now left is sort of pure and can now leave as pure iron. Okay, after you remove the slag. طيب. The liquid slag falls to the bottom of the furnace and floats over the molten iron because it's less dense. Thus, it prevents the reoxidation of the molten iron. So, this is the first advantage that the liquid slag has, other than it purifying the iron. The second advantage is that it prevents the reoxidation of the molten iron. طب انت خلص, you ended up with your iron. We're happy. We got our iron. طب okay, there's still air going in, so there's still a chance that oxygen will react with this iron and oxidize it and make it Fe2O3 again. وهلا you're back to step 1, you're back to square 1, you just lost all the progress you made. So another advantage of the slag is that it rests, since it's less dense, it rests on top of the iron, preventing the reoxidation of the iron that's down here. Okay? طيب. The slag is tapped off separately. Once solid, it is used in concrete to make buildings and roads. So this is a third advantage. It's used in concrete to make buildings and roads. Hot waste gases escape from the top and are used to transfer heat to the incoming air. This helps reduce the cost of the extraction. So they keep it open here so that the gases that you are using can go up and heat up the surrounding air, which reduces the cost. So now you don't have to heat as much air as before. Okay, iron extraction runs continuously and is much cheaper than electrolysis. Okay, this is just another summary of what goes on. Uh, as you can see here, it's happening at 1500 degrees Celsius, 700, whatever. Okay, these are just the reactions, again. So it starts with carbon plus oxygen to get carbon dioxide. And this carbon dioxide reacts with more carbon to produce carbon monoxide. And this carbon monoxide reacts with Fe2O3 to get Fe and carbon dioxide. And then the CaO from the calcium carbonate decomposes to calcium oxide. This calcium oxide reacts with the Si2, the sand, to form calcium silicate, which is otherwise known as slag. You need to know that the iron obtained at the end is around 95% pure and is what we call pig iron, or other people call it cast iron. Okay, you need to know this name in case it comes. What is pig iron? Pig iron is the iron obtained from the blast furnace. Okay, in addition to the element iron, it contains, we said it's 95% pure. Where is the other impurities? There's 4% carbon, sulfur, silicon, and phosphorus. You must know this. Okay. Most of the cast iron is purified further and turned into different types of the alloy steel. So iron is very rare you see iron in its pure form. They use iron usually in what we call alloys. What are alloys? Alloys are a mixture of two metals, which we will cover more into detail in, I think, 3 pages or 4 pages. Yeah, here. Okay. طيب. We're going to talk about alloys in a bit, but iron, you will use iron in alloys. Type. What are some properties of this pig iron that is produced? It's hard, but it's very brittle, so it breaks easily if you pressure it, okay? Which is very common. I think with iron, you guys know that iron is not very strong. It corrodes very easily. What is corrosion? Yeah, it rusts. We know iron rusts. So these are properties, these are sort of disadvantages. What are the uses of cast iron? We don't really use cast iron. It's very limited because, like we said, it corrodes very easily. It rusts easily. So therefore, cast iron is usually used in making very large objects like bridges, buildings, and ships. It's also used in making pots and pans because it conducts heat very well. But usually we use it as an alloy. Okay, but these are the uses that you may use the cast iron for. Okay, most iron is extracted by reducing iron ore, hematite, by carbon monoxide in a blast furnace. What are the raw materials added to hematite? What other than hematite do you need? We need coke and we need the limestone, right? So let's take a look at grid 30. So you need coke, limestone, otherwise known as calcium carbonate. Okay, did they say, yeah, calcium carbonate? You could say limestone as well. And air. Of course you need air, guys. You need to open the furnace, right? The furnace is open. Air will come inside. Not like that. A series of reaction occurs in the blast furnace. Describe these reactions. Okay, what's the first reaction? Let's write them down one by one. The first reaction, remember, coke plus the air, the oxygen from the air to produce CO2. What's the second reaction? CO2 will react with more coke to produce 2CO. Now, our iron is ready to react. So our hematite, Fe2O3 plus this CO will produce Fe plus carbon dioxide. So it's 2Fe and it's 2CO2. هون عندك, wait, I think you put the 2 here to make this 6, 7. hold up. Okay, هلا عندك, hold up, let me try balancing this. Why can't I don't know why I can't balance. Why did I erase this? Fe2O3 plus CO to produce Fe plus CO2. طب 1 second. Okay, I think this is balanced. 3, 2, 3. Fe2O3, you have 2 irons, 2 irons. You have 3 oxygens here and 3 oxygens here, so it's 6. And then you have 6 oxygen. Okay, that's balanced. And then the 3 carbons, 3 carbons. Okay, yeah, this is balanced. Type. This is the reactions that extract the iron. And then if they asked about the ones to do with the purification of the iron to produce the slag, what's the first thing? The calcium carbonate, under the heat, it decomposes to get carbon dioxide and CaO, right? And then the CaO goes and reacts with the sand, the SiO2, the silicon dioxide, to produce CaSiO3, the slag. right? So these are the full set of 5 reactions. Okay, so yeah, as you can see here, these are the 5 reactions. طيب, what is, okay, where are we? What if they were to describe this would be coke being burned to form carbon dioxide, and the carbon dioxide being reduced by more coke. Okay, and then hematite is reduced by the carbon monoxide. Okay, and then limestone decomposes to form calcium oxide and carbon dioxide. Just, you're just talking about what's happening in the reaction. Then calcium oxide reacts with silica to produce what we call this slag. What is cast or pig iron? CQD24. What is cast or pig iron? It's the one extracted from the blast furnace, right? So it's the iron that is obtained from the blast furnace. What is the impurities it may have? It's 4%. It's, remember, we said that this is 95% iron. 4% impurities like what? Sulfur, phosphorus, and I think it was nitrogen and potassium. I'm not sure, wallah. Let me see. I'm not gonna محألف. How much is it? It's 4% sulfur. Oh yeah, so sulfur, silicon, and phosphorus. What were the ones here? Sulfur, silicon, phosphorus, and carbon as well. Okay, yeah, it makes sense to have silicon in the impurities, right? Why? Because أصلا we said that the major impurity was SiO2, the sand. So أكيد one of the impurities is silicon. Okay, and you're reacting it with coke, carbon. So أكيد there's going to be some leftover carbon. So that would be one of the impurities, as well as phosphorus and sulfur. They're pretty, you have to memorize these. Corrosion and rusting. Okay, corrosion is the process by which a metal reacts with the oxygen of the air in the presence of water. It has to be in the presence of water to produce an oxide layer. Chemically, you should know that corrosion is a redox reaction. Anyways, what is important here? What is corrosion? Corrosion is the rusting, right? It's rusting. In iron, it's called rusting. You guys know when you have iron, and you put it into contact with water and oxygen, it's gonna rust, right? So we should know it's a serious problem, and large sums of money is spent annually to protect them. We discussed earlier that aluminium also oxidizes, but does it fully rust? No. Remember, aluminium, when it oxidizes, it forms a protective layer of this oxidized layer, and this prevents further oxidation. However, iron, it rusts, which spreads like a disease in the metal. Okay, so it continues inside. Okay, طيب. Unlike the iron oxide, the aluminium remains stuck to the metal and it protects it from further oxidation. What two chemicals are essential for rusting to take place? What do you need for something to rust? Oxygen and water. Pretty self-explanatory. Water and oxygen. Okay, there are many ways for rust prevention. To prevent iron rusting, how do you prevent rusting from happening? You have to prevent oxygen and water from coming in contact with the iron. Because what causes the rust? The oxygen and water. If you can prevent that oxygen and water from coming into contact with the iron, then you can prevent the rust, right? So the first method, they call them barrier methods because they prevent the oxygen and water from coming into contact. The first one is painting. Ships, lorries, and cars, they use painting. But you need to pay attention that the paint can be scratched, so you need to check it regularly. The second one is oiling or greasing, okay, especially with machines and vehicles. The oil also must be renewed regularly because it's gonna dry up eventually. And then the third is coating with plastic. The exteriors of refrigerators, freezers, and many other items are coated with plastics such as polyvinyl chloride, PVC, to prevent the steel structure from rusting. So they cover it with plastic. So these are the barrier methods. They usually come multiple choice. Maybe she might get you suggest one way to prevent rusting. You would say paint it. Very easy. You answer the full mark just by saying painting. The second method is electroplating. If you remember, it came in written actually in the term 1 final, is what is the purpose of electroplating? Suggest one purpose or one effect of electroplating. Why do we electroplate? And it's actually to prevent corrosion. Why? Because you coat it with a protective layer when you Ya Allah, when you electroplate. Okay, so مثلا cans for food can be made from steel coated with tin. We coat it with tin, we deposit like the tin goes on the steel and it protects the steel from rusting. Okay, so the first way is they dip the steel into molten tin. The second way is through the electroplating method that we all know. Okay, so galvanizing is the process of covering iron with a thin layer of zinc by either dipping it into molten zinc or electroplating it with zinc. So galvanizing has to do with zinc on iron. Okay, what does galvanization do? It prevents iron from rusting in two ways. The first way is the zinc is the one that takes all the water and oxygen. And the second one is that since zinc is more reactive, if it comes into contact, then it's gonna be oxidized instead of iron. For example, steel girders used in the construction of buildings and bridges are galvanized by dipping into molten zinc or electroplating with zinc to prevent them from rusting. If the zinc layer is scratched, the protection will not stop. As long as some zinc remains in contact with the iron structure, the structure will be protected from corrosion as the more reactive zinc corrodes in the place of iron. This is what I'm going to explain now. Sacrificial protection. If you have a plate or a spoon, okay, هيك عندك spoon, صح? This is made out of iron, so it's gonna rust. What if أنا جيت جبت لك wire and I connected this to a yellow zinc plate? What's gonna happen? If this comes into contact with oxygen and water, it's not gonna rust. Why? Because this zinc, it's gonna see it. It's gonna be like, oh, it's coming into oxygen and water. I'm gonna sacrifice myself for this iron. So basically, this is what we call sacrificial protection. When you connect your metal to another more reactive metal, that's gonna take it's gonna sacrifice itself for the less reactive metal and react with the oxygen and hydrogen. Even if this metal is scratched, even if this metal is only one gram, if it's only 1 gram, it's still gonna react until it's completely worn out. Okay, so the sacrificial protection is a process of attaching a piece of metal such as zinc or magnesium to protect them from rusting. The more reactive metal will react with oxygen and water and sacrifice itself for the iron. Bars of zinc are attached to hulls of ships and to oil rigs to protect them from rusting. When the zinc runs out, it must be renewed. That's the only disadvantage. Gas and water pipes made of steel are connected by a wire to blocks of magnesium to obtain the same result. So, like I told you, you can use zinc or magnesium. List 3 methods to prevent corrosion. What are the 3 methods? أول وحدة is the barrier method. Okay, the second was sacrificial protection or electroplating. So let's take a look. 33. So cathodic protection or sacrificial protection, where the metal is connected to a more reactive metal. List 3 method, is this the same? That's the first one. Cathodic protection or sacrificial protection, that's the first one. Electroplating, where the metal is coated with a non-reactive metal such as tin. And galvanizing, where the metal is coated with zinc. Okay, so sacrificial protection, where the metal is connected to a more reactive metal. Electroplating and galvanizing. Here they said, I don't know why the barrier method is not mentioned here, but it should be correct as well. Okay, so they said electroplating, galvanizing, where the metal is coated with zinc. Galvanizing, you dip. Why am I using yellow? You dip in molten zinc. Okay. Electroplating is where you use basically electrolysis, which I will cover in a bit. Electrolysis to cover with metal, right? And then the cathodic protection is you just connect it to a more reactive metal that will sacrifice itself. Okay. Okay, CQD 39. Aluminium is more reactive than iron. However, it is used in many applications such as satellite dishes and ladders without any coating or protection. Explain why. Even though aluminium is more reactive than iron, you would expect it to rust, right? But why does aluminium not rust? Remember, we have one property of aluminium, and that is that aluminium will form. It's gonna react and rust, but it's only gonna form one protective layer. Okay. So aluminium is very reactive in air to produce aluminium oxide that coats the aluminium. Since this oxide layer is inert, it protects aluminium from further corrosion. So like we said, aluminium will rust, but only on the outside, so it's going to protect it from, it is going to protect the rest of the metal from rusting. Okay, how long is this recording? 1 hour 9. Okay, uses of copper. Okay, the first use of copper in electrical wires, in alloys, and in steam boilers. Why is it used in wires? Akid, because it's highly ductile and it's a good conductor. Why is it used in alloys? Because it's hard and it resists corrosion. As well as where is it? Yeah, statues and whatever. In steam boilers, cooking utensils, and water pipes. Why would be used in a boiler? Obviously, because it conducts heat. Why would be used in a cooking utensil? Because it resists corrosion. So list 3 uses of copper. CQD 22. Copper is used in production of wires, alloys, and ornamental works, such as these, whatever, ornamental works. Okay, alloys. I think this is the last thing we have in this chapter, other than extraction of aluminium. Okay, yeah. So we're almost done. Alloys. Type. Alloys, you should know, is just a mixture of 2 or more metals. Okay, it may contain non-metals as well. Okay, basically you melt 2 metals, you mix them together, you get an alloy. Okay, just like a mixture of 2 metals. Mixing atoms of only slightly different sizes disrupts the regular packing and makes it much more difficult for layers to slide over each other when a force is applied. This is what makes alloys harder and stronger, but more brittle than the individual metals that make them up. Alloys are still metals, and so we expect them to exhibit all the properties of metals. So basically, you mix atoms of a bit, metals that are only a bit different in size. Okay, this will disrupt the packing and make it so much harder for them layers to slide. Okay, oh my god. Okay, so here they're talking about what's beneficial about alloys. The first benefit and advantage is that it has more useful properties. Like what? For example, brass is copper and zinc. You should know that it's harder and more corrosion resistant than either copper and zinc. So when you mix them together, it's going to get you the same properties, but it's just a bit harder. It's harder to break, and it's more corrosion resistant, so it won't rust. Of all the alloys we use, steel is perhaps the most important. Many steels have been produced, okay? They contain not only iron, but also carbon and other metals. Steel is like iron, but that doesn't rust. Like most cutlery, forks, spoons, knives, are made of stainless steel that doesn't rust, okay? For example, nickel and chromium are the added metals when stainless steel is produced, you see? The chromium prevents the steel from rusting, as chromium forms an inert oxide layer, while the nickel makes it harder as it has different atomic size than iron. So this is just talking about, what are the benefits that can come from alloys. Usually they're harder and more corrosion resistant. That is the main advantage. What are some properties of steel? Steel is the ones we use with our forks, knives, and spoons. It's less brittle, so it won't break as easily, and it's more resistant to corrosion. If steel was not corrosion resistant, do you think we're going to use it as our forks? Do you think we're going to eat with the rusty forks? Obviously not. These are some types of steels and their uses. بس هبل. Mild steel, hard steel, stainless steel. Okay, stainless steel is the best one. It has iron, nickel, and chromium. You should know that you add nickel and chromium to the iron, as well as carbon. Okay, so you're always adding carbon, but for stainless steel, you're adding nickel and chromium. So here, for mild steel, 0.5% carbon, the rest is iron. Okay, you'll use it for car bodies and machinery. Okay, because we don't really care if this rusts a lot. For hard steel, 1.5% carbon, the rest is iron. And you use hard steel, it's hard, so use it for cutting tools, razors, and blades. Stainless steel has Fe, nickel, chromium, and carbon. Okay, stainless steel, obviously you're going to use it in cutlery. That's the first thing, because we don't want it to rust at all. We need it to be stainless, literally. And surgical equipment. You can't have any rust in your surgical equipment, because if your surgical equipment is rusty, the person you're doing the surgery on is gonna die. Okay, so why is it used in these? Because of its hardness and resistance to corrosion. أهم شيء resistance to corrosion. Okay, high carbon steel are strong but brittle, and low carbon steels are softer but more malleable. Anyways, la. Which of the following statements describing alloys is false? Okay, alloys are harder than the metals they are made from. Alloys are cheaper than the metals they are made from. Alloys are good conductors. Alloys are a mixture of metals. Alloys can be molded into different shapes. I think E is looking like it's false صراحة. B really? Alloys are cheaper than the metals they are made from. Okay. Okay. Okay, I think that's false. They should be more expensive. Why is it more expensive? Because it's coming from two metals, so it should be more expensive. I think that's why. That makes sense. Okay. And شكله it can be molded into different shapes. They're malleable. Oh yeah, you can make it into knives, into cars, and whatever. Okay, one of the alloys of iron is stainless steel. Stainless steel is more expensive than steel. It resists corrosion and is harder than it. Which of the following is made of steel? Saucepans, cutlery, pipes in a factory, cooking utensils. Okay, it's all of the above, right? Yeah. Part B. Cutlery is made of stainless steel while food containers are made of aluminum. What is a property possessed by both metals that make them suitable for the specific use? They are both what? Obviously, it's going to be resistant to corrosion. Why? And if you want to store food, are you going to use something that rusts? Of course not, right? So what makes it suitable for storing food? They resist corrosion. So B. Okay, describe the structure of alloys and why are alloys used instead of pure metals. Okay, describe the structure of alloys. I'm just going to show the solution. Alloys, it's a solid solution of a metal with either other metals or non-metals. So it's just a solution of metals, right? The added atoms can either replace some of the host atoms in the lattice or occupy the interstices between neighboring atoms. Okay, I didn't explain how it forms. Over here, you have, this is the normal one. This is the normal metal. Okay, you add another metal and you see these spaces, the foreign atoms will occupy these spaces. This is what causes it to be so hard. Okay, so that is the structure of an alloy. Okay, so over here, grid 31, you should know this. It's a solution of metal or other metals. You should know that the added atoms replace the host atoms or occupy the holes between the neighboring atoms. Okay, so they either replace the host atoms or occupy the spaces. And that's how it forms. That's what makes it hard. Why are alloys used instead of pure metals? Because they're harder and they're less corrosive, right? So alloys possess desired properties that aren't found in pure metals. For example, pure gold is a soft metal and therefore is not desirable when making jewelry. So, actually, by the way, the gold you buy isn't pure gold, right? It's mixed with copper, which is what makes the gold you buy hard. Okay? So this is why you use alloys, because it produces desired properties that we want, such as harder and less corrosive. Okay. So she can ask this now, since it's in the course division, she can ask about the gold. Okay. Now electroplating. We're not gonna go. I'm not gonna spend too much time on it because basically electroplating we've done it. Electroplating we've done it before. I hope my mic isn't too out. One second. Okay. We did it already in chapter 4 with the redox reactions and the electrolysis chapter. Electroplating is a process of covering a metallic object with metal using electricity for more attractive appearance, and what we care about here is the protection against corrosion. What is the steps? Obviously, the object to be electroplated is at the cathode, okay? And the metal that you want to electroplate with is at the anode. You should remember that the cathode is the negative terminal and the anode is the positive terminal. The electrolyte is an aqueous solution of the metal to electroplate. So the solution it should be in has to be an aqueous solution of the metal. For example, is the chromium plating of a tap. If you want to play chromium plating of the tap, you want to plate the tap so the tap goes at the cathode, which is the negative terminal. The chromium bar would go to, or rod would go to the anode, which is the positive terminal. Okay, and the solution would be anything that has chromium, any soluble solution of chromium. That would be your solution. What are some details to note? A clean surface of the object is needed to ensure that the metal layers stick properly to the object. Rotate the object from time to time to ensure that the object is uniformly electroplated, and dip the object deep into the electrolyte to ensure that the entire object is being electroplated. Okay, CQD 28, draw a labeled sketch of the apparatus that may be used to electroplate an object with silver by electrolysis. Write the equations for the reaction that will take place at each electrode. So this reaction part is what we care about. Let me try drawing it. أول شيء, let's draw a labeled sketch. So أول شيء, we want to electroplate any object, let's say a spoon. Okay, that's easy to draw. So you'd have the battery, you'd have the positive side and the negative side. Remember that if you want to electroplate the spoon, that means the cathode should be what the thing you want to electroplate. So the cathode will be the spoon, and we want to electroplate it with silver. So at the anode would be my silver rod. Okay, this the cathode is negative, and the anode is positive. Type. So over here we have our spoon. Let me draw it in black. Okay, وهيك it's my spoon. Okay, and over here we have our silver rod at the positive terminal. Let's say silver rod هيك. Okay, I think it should be in the solution. I don't know why I didn't draw it in the solution, so let me fix that. Okay, let me continue it down here and put the هيدا all the way in the solution. Should be all the way in the solution. Okay. 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 ماشي. You should label the terminals. هون is the positive terminal, or you can put maybe anode if you want. هون you label it negative, or put cathode if you want. Okay, you should label the solution. We want to plate it with silver. Okay, let's label the silver rod. Well, this is our spoon. Let's say we want to plate it with silver, so the solution should contain silver. Always the easiest one is a nitrate solution. So you could say silver nitrate solution. Always the easiest way is just say the name of your metal and put nitrate, nickel nitrate, chromium nitrate, whatever. It's always easy to use nitrate because nitrate will always guarantee solubility. Anyways, silver nitrate solution. What are the equations for the reactions that will take place at each electrode? At the cathode, we have reduction, right? We have reduction. Remember red cat. So at the cathode you always have reduction. And what's reduction? Reduction is the gain of electrons, right? Reduction is the gain of electrons. Oxidation is loss of electrons. Reduction is gain. We're working with silver. So Ag is Ag plus, right? You're gonna gain an electron, right? To produce what? Ag solid at the cathode. So aqueous. At the cathode, what's gonna happen? These Ag ions will gain an electron and go onto the spoon as a silver metal layer, solid silver layer. Okay. At the anode, however, the silver metal will be oxidized and lose an electron to become an ion and float in the solution, so that this ion will later go and be attracted to the spoon over here and gain an electron, so that it turns back into silver metal and forms a protective layer on the spoon. So at the anode, what happens? The rod is oxidized and these solid particles will dissolve and become silver ions. So your Ag solid, its oxidation is loss of electrons, so your electron will be lost. It's going to turn into what? An Ag plus ion. Okay, aqueous. So your solid silver will dissolve into the solution, become an ion. And then at the anode, then at the cathode, that ion will regain that electron and become a solid silver and form a protective layer on the spoon. This was covered in chapter 4. Okay. Anyways, so this is just an example. Extraction of aluminium. Okay. Similar to the extraction of iron, the extraction of aluminium. Aluminium makes 8.1% of mass. Aluminium is highly reactive, but it's masked by an oxide layer. Aluminium spontaneously reacts with oxygen to produce aluminium oxide, which strongly adheres to the surface of the metal. We know this. We said aluminium forms the oxide layer and protects it. Aluminium is the second most widely used metal after iron. Okay, this is what you need to know. The main ore from which aluminium is extracted is called bauxite. Okay, which is Al2O3. It's aluminium oxide, Al2O3. The ore is first mined, then purified, and then finally melted and electrolyzed. Okay, what is the ore? Bauxite, which is composed of mainly aluminium metal, along with iron oxide and other impurities. So what are the impurities in bauxite? Iron oxide is one of them. Right. You should know bauxite, it's amphoteric, while Fe2O3 is basic. This is one of the impurities, right? So the first thing the ore is treated with is sodium hydroxide. So your bauxite ore is treated with sodium hydroxide. Since Al2O3 is amphoteric, is it going to react with the basic sodium hydroxide? Yes. So the amphoteric Al2O3 will dissolve in the NaOH to form sodium aluminate. Okay? While the basic Fe2O3 does not, right? Like we said, the bauxite is composed mainly of aluminium, but it has an impurity of iron oxide, the Fe2O3. Okay? And is separated by filtration. So just like this, you got rid of the first impurity, which is iron oxide. Because remember, when you want to extract a metal, your goal is to remove all the impurities. So the first impurity, the iron oxide, how is it removed? Since iron oxide is basic, the Al2O3 will be able to react with sodium hydroxide, but the iron oxide won't. So after it reacts, you can just filter out what's left, which would be the Fe2O3 that did not react. Okay, so that's the first step. Okay, so the first step, Al2O3 dissolves in NaOH, while the basic Fe2O3 does not and is separated by filtration. So that's the first thing. So you got rid of your first impurity. This alumina, okay, or sodium aluminate, it's not soluble and has a melting point of 2017 degrees Celsius. So it is dissolved in molten cryolite, Na3AlF6. You need to know the formula. It came multiple choice. Okay, what is the formula for cryolite? It's Na3AlF6. Okay, so since aluminum is such a high melting point, they dissolve it in molten cryolite. What does this cryolite do? It acts as a solvent and it reduces the melting point from 2017 to around 800 to 1000. Some people say 950 degrees Celsius, which is correct as well. So since it decreased the melting point all the way about 1000 degrees, obviously this is going to save on the energy costs, right? So it's going to be way cheaper to melt it. I won't have to buy a furnace that holds 2017 degrees Celsius. I can just use one that holds 900 degrees Celsius. The molten liquid is then electrolyzed in a cell using graphite electrodes. The process runs continuously with liquid aluminum removed and more alumina added. Okay. So you now have this alumina. Okay, it's not soluble, but its melting point is so high. So after you remove the Fe2O3, its melting point is so high. So they add molten cryolite to reduce the melting point to 800 to 1000. So you now have a molten liquid. What they do with it? They electrolyze it. So when you electrolyze something, what happens? You end up getting, at the cathode you get the metal, or at the anode you get the gas, right? So at the cathode in this case we're gonna end up getting the aluminum. So the molten liquid, the alumina, the leftover alumina, okay, it's gonna be left over. How do they electrolyze it? They use what electrodes? Graphite electrodes. This comes in the Ca. Okay, you need to know it's graphite electrode. Okay, so what happens? You have at the first at the anode. At the anode, remember you have oxidation. Oxidation is loss of electrons. Okay, alumina is Al2O3. Okay, not Al2O3, but you have aluminium and oxygen. I think, right? Yeah, it's Al2O3. Yeah, so you want to electrolyze it. At the anode, you're working with the anion, the oxygen, right? At the cathode, this is cathode. This is anode, right? At the anode, you have oxidation. It's loss of electrons. So you have O. You're gonna form oxygen gas, right? So you have O2 minus. You're gonna form oxygen gas. Okay. Since it's at the anode, so you have oxidation. So you're losing electrons. So is the electrons gonna be here or gonna be here? You're gonna be losing electrons. So you're gonna be giving off the electrons. So E minus is gonna be outside. And I know many people they get confused when I write down the reactions. Okay, let me write the cathode reaction first, and then I'll do the anode. At the cathode, the aluminium, the cation goes to the cathode, the oxygen goes to the anode. Okay, at the cathode you have reduction. Remember, red cat. Reduction is gain of electron, right? So you have Al. Al is what? 3 plus. Okay, you're gonna gain electrons. How many electrons am I gonna gain if it's 3 plus? 3 to produce Al solid, or no, liquid actually. Why liquid? Because it's molten. We're working at very high temperatures, so it's molten. Okay, so you have this. You want to end up with aluminium, and you want to end up with oxygen gas. Once you know your products, it's very easy. So this is at the cathode. Very easy. But I don't know why they multiplied by 4. I really don't know. I think because the overall reaction, you get 4 aluminium, but they multiplied this by 4, and therefore this becomes 12, this becomes 4. Okay? And then at the anode, we know oxygen gas is being produced. So you have O2 minus, you're producing oxygen gas type. You have oxidation at the anode, so you're going to lose electrons. How many electrons am I going to lose to get for 2 minus? How many am I gonna lose? 2 electrons. Okay, but I only have one O here. I have 2, so I have to multiply this by 2. Multiply this by 2, it becomes 4. Okay, so 2O2 minus to release this. Okay, again they multiply this by 3. I don't know why. Well, Bella, I know why, because the overall reaction we produce 3O2. But it doesn't matter. If you just try this, is gonna be fine. Anyways, to summarize. Okay, to summarize. What do you need to know about the extraction of aluminum? You need to know the first step is that this. You need to know this. This is your first step. Okay, what comes in CAs? You need to know that its original boiling point as melting point is this. You need to know this. You need to know that you dissolve it in molten cryolite. Okay, and this is its formula. You need to know its formula as well. You need to know that it reduces the melting point from this to this. You need to know this. Okay, and you need to so that this saves on the energy. These are all CA questions that came. It was one huge question. I think its weight was 5 or 6, and these were all the parts in it. You should know that it's then electrolyzed using graphite electrodes, and then the reactions you need to know. Okay, you need to know. I think they only asked about the overall reaction in the CA. Okay, the overall reaction is the most important one, but if they ask for at the anode and at the cathode, you need to know how to do it. Okay, but the overall reaction, to write the overall reaction, you should know that alumina, we're working with Al2O3. Okay, Al2O3, you want to purify it, so you're splitting it into aluminium and oxygen. Okay, balance it. You have 2 aluminiums, so here you're going to put 2 aluminiums. Okay, you have 3 oxygens here, so you're going to multiply this by 2, so you have 6, so here you have 3, and then you're going to multiply this by 2, so it's going to be 4. So this is how your reaction looks. Okay, this is the overall reaction. Once you have the overall reaction, writing the anode and cathode reaction will be very, very, very easy. Okay, at the cathode, you have reduction. Reduction is gain of electrons, so aluminium, it's going to gain electrons. Remember, you have 4 aluminiums, so we're going to multiply this by 4. 4 times 3 is 12, so you're going to gain 12 electrons to produce 4 aluminium salt. And then at the anode, you have this being produced. So you're starting with O2 minus, you have what being produced? Oxygen gas, for 3O2 being produced. So you have 6 here, so you're going to have 6 here. I don't know why I didn't put the charge. You always ask yourself what's being produced, and I always fill in what I'm starting with, what's being produced. When I know what's being produced, it's very easy to write the rest of the reaction. This is just how I work. Okay, and I know oxygen gas is being produced, so I write O2 first, and then that means I'm starting with O2 minus. Okay, then just fill in the electrons. Anode is oxidation, so oxidation is also electrons, so you're going to release how many electrons? 6 times 2 is 12, so 12 E minus. Okay, this is gas, obviously. This is aqueous. Liquid, never mind, liquid. They start as liquids because it was molten. Anyway, I think this is it's not very easy, but it's not that hard. Okay, so it's just specific points you need to know, nothing too hard. You need to know this, okay? Oxygen produced at the anode reacts with it, producing carbon dioxide and carbon monoxide. Since it's producing these, the electrode has to be, the anode has to be replaced periodically. You need to know this. This came, I think, in the CA as well. Okay? You need to know that oxygen produced at the anode will react with it, producing carbon dioxide and carbon monoxide, so you have to replace the anode periodically. What do you require to extract aluminum? Obviously, you need a source of electricity, preferably hydroelectric power. Okay? I think my voice is very... it's giving me red. Sure, it gives me red. I don't know how the red sounds. Is it... does it hurt your ear? Or is it fine? I don't know. Source of electricity, obviously you need a source of electricity, preferably hydroelectric power. Okay, the process uses a great deal of electricity and is not cost efficient unless the electricity is cheap. So that's why you use hydroelectric power, because it's renewable. Large supply of cooling water. You need to be able to cool all of this because there's a lot of temperature there's a lot of high temperature stuff going on. Obviously, you need the raw materials, which are bauxite and cryolite. Remember, what's bauxite? Bauxite is the aluminum ore. Cryolite is the Na3AlF6, right? Was it Na3AlF6? Yeah. The cryolite, the thing that you add to lower the melting point. A good transport system, you should be able to transport this aluminum. And waste gases purification to get rid of the carbon monoxide and carbon dioxide produced at the anode. Remember, we produce these, and you will always want to get rid of this. Okay, question 35. What chemical is used to manufacture aluminum industrially? What do you mean? Do you mean, I think you mean cryolite? Let's see, CQD 35. Okay. To manufacture aluminum industrially, you need molten aluminum oxide. Okay. What is the formula and common name of the aluminum ore? Aluminum ore is called bauxite. What's its formula? It's Al2O3 dot 2H2O. Okay, for the bauxite, this is the bauxite, Al2O3.2H2. This represents the impurity in the bauxite ore. Remember, we have impurities in it. I think this 2H2O represents the purity. But they never ask this stuff, yani. They really never do. Okay, so to manufacture aluminum industrially, you need molten aluminum oxide. That's the chemical. The ore is bauxite. The name of the oxide is alumina. What's the oxide? How do you get the oxide? You get the oxide after you react this with the sodium hydroxide. If you remember, go up. Okay, so you get sodium aluminate. They also call it alumina. When do you get it? You get it when you dissolve the bauxite with sodium hydroxide. But they didn't. She didn't ask what's the name of the oxide. Why are they giving me the name of oxide? I don't know. Man, this is the CQD. The students for the CQDs, they really, they PMO والله, they piss me off. بس خلاص, we're forced to go along with it. What is added to the aluminum ore to remove the impurity that is present along with it? We said sodium hydroxide. Yeah. Let me see if they said something else. Yeah, sodium hydroxide solution is added. So to remove the impurity, what do they add? Remember, they add sodium hydroxide. Okay. What is added to aluminum ore to lower its melting point? We said it was cryolite, Na3AlF6. What is the function of cryolite? To lower its melting point, right? So it lowers the melting point of the electrolyte, and it dissolves the Al2O3. Huh? So it has two. So if you see in the written part, a 2-mark question, what is the function of the cryolite? They want two. The first is that it acts as a solvent, so it dissolves the Al2O3, the ore, and the second is that it lowers the melting point. So it has two things. Okay. At around what temperature will the process take place? At around 1000 degrees, right? So from 800 to 1000. So we just set the furnace at 1000. And what is the overall reaction for how aluminum is produced? You have the ore, the alumina. It's broken down into aluminum and oxygen, right? Al2O3 broken down to aluminum and oxygen. Like I told you, this is what they usually ask. Okay, this is the overall reaction. Aluminum is produced industrially by electrolyzing its oxide. Okay, what raw material is used at the electrolyte? What other raw material is used to lower the operating temperatures? Okay, what raw material is used at the electrolyte? Let's see. So the raw material that we use is bauxite, right? That's how we use bauxite. That's what we're starting with. That's the raw material. Okay, and what is used to lower the operating temperature? To lower the temperature, we use cryolite, right? Na3AlF6. Yeah. Okay, so used at the electrolyte, what's the raw material? Bauxite, Al2O3.2H2O. And what is used to lower the operating temperature? It is the cryolite. What type of energy is used in electrolysis? It should be electrical energy. Yeah, electrical energy. It's electricity. State the materials from which the anode and cathode are usually made. Okay, they're usually made from inert materials, huh? From graphite. They ask this. I think they have to. I think they asked this in the CA. It was graphite, yeah. They're made up of graphite. Don't say platinum, because or any inert material, because for the extraction of aluminum specifically, it has to be graphite. But they asked it in the CA. Why does the anode have to be repeatedly replaced? Again, they asked this question in the CA. Okay, the anode being made of graphite, it reacts at very high temperatures with the oxygen, being produced at its vicinity. So basically, you need to know that since there's carbon dioxide being produced due to it reacting with carbon dioxide, the anode has to be replaced frequently. Remember, the anode, the electrolyte, the electrodes are made out of graphite. Okay, what is graphite? Graphite is carbon, right? These carbons will react with the oxygen and form carbon dioxide. So the carbon that makes up the platinum, the graphite rod, the graphite electrode, will begin to dissolve slowly because of its reaction with oxygen. Therefore, you must replace the electrode frequently, okay, so that it doesn't dissolve. CQD38, aluminum is extracted by the electrolysis of molten aluminum oxide dissolved in cryolite. A schematic diagram is shown below. Positive electrode, whatever, negative electrode, very simple, molten mixture of aluminum oxide and cryolite, and then aluminum. Give two reasons why the electrolysis is done using a molten mixture of aluminum oxide and cryolite instead of just solid aluminum oxide. Why do we use cryolite? Actually, because cryolite dissolves, because the cryolite acts as a solvent for the aluminum mixture, and it lowers the melting point. So let's see. Aluminum oxide is ionic compound, so it does not conduct electricity unless molten. And to make it more, since the melting point is very high, it is lowered by adding cryolite. Lowering the melting point allows to lower the cost of the extraction of aluminum. So they gave you three reasons. So why it's done using a molten mixture? Why is it done using a molten mixture? Since it's an ionic compound. Guys, remember, electrolysis of ionic compounds, they need to be either aqueous solutions or molten. But in this case, you can't make it aqueous. You need to make it molten. So since aluminum oxide is ionic, it has to be molten. And why with cryolite? Obviously to lower its melting point, to lower the cost. This was, I think, multiple choice. Okay, to lower the cost. So aluminum oxide is an ionic compound, so does not conduct electricity unless molten. Since the melting point is very high, it's lowered by adding cryolite, and lowering the melting point allows to lower the cost of extraction of aluminum. Give the ionic half equations for the reactions occurring at the electrodes. So this one we did this previously. Remember it's Al2O3, we're producing oxygen and Al, right? Type. What is happening at the cathode? I always start with the cathode. Cathode, we're producing Al, right? At the cathode's reduction, so it's gain of electrons. So you have Al3 plus, we are gaining how many electrons to produce Al? 3 electrons. But since we're producing 4 aluminum in the reaction, you put 4, this becomes 12, this becomes 4. Okay, so let's take a look. Is that correct? Okay, they don't care, but this is correct. But putting it without the 4 is also correct. Exactly, this is why I was telling you earlier, you don't have to multiply by 4. So Al3 plus 3A minus to produce Al. You can make that. And then obviously at the anode, you have oxygen being produced. You're starting with what? O2 minus. Okay, at the anode, you have oxidation. Oxidation is loss of electrons, so you're going to have 2 minus over here. But to balance 2, so you have to put a 2. So you need 4 electrons now. Okay. I don't know, I feel like many people struggle with writing these reactions, but really you need to get the hang of it. خلاص. You're going to see many questions like these. Is there anything else in the solution? No. Okay. The anodes made up of graphite have to be replaced regularly. Why? Because the carbon inside the electrodes because the carbon inside the electrons react with the oxygen that will dissolve it, right? So the carbon in the graphite will react with the oxygen to form carbon dioxide gas, so it's going to start dissolving. Okay, we're almost done. Just one more page. What are uses of aluminum in cooking utensils and food containers? Why? Because they resist corrosion, they have low density, and they conduct heat well. Also for making aircrafts, because they have low density, so they can fly, and they have high tensile strength, so they can withstand high pressure. They are also used in steel cored aluminum cables, so steel core, or overhead power cables. Why is it used? Obviously, if you're using it in a cable, then it's a good conductor of electricity, and it has low density, less dense than copper that was previously used. Steel is used because it expands less than copper and has a high melting point, so it won't melt. Remember, when manufacturing wires, this goes back to physics, you need a wire that doesn't melt easily, because there's going to be resistance in the wire, and if it melts easily, then the wire will melt. and you won't be able to build a circuit. So you would prefer one that has a high melting point. These are all properties that they could come in multiple. The steel is used to support aluminum, which is a very good conductor. Okay, recycling aluminum requires around 5% of the energy needed to extract it. That's why it is imperative to recycle aluminum. Fill in the table to determine the property related to each of the given usage of aluminum. Okay, they answered it for you. In planes, why do they use it in planes? Because it's low density. In cooking utensils, because it's good conductivity, right? In electrical wiring systems, because it conducts electricity and it's malleable. In food packaging, because it's unreactive, it doesn't corrode. You can say this for food containers, resists corrosion. Okay. Building industry, because it's strong, lightweighted, and shiny. Okay. The rest of these are all past paper questions, which I won't be covering. So that being said, thank you so much for watching and good luck.